Okay, share screen. Let's try this one more time for number 9. So again, here is the surface. Here's a cart. And she pushes it at 29 degrees below. So we're actually going to have to look at it like this. So that's the applied force that you're pushing towards it. So FAP-Y is actually pointing down. Here, FAP-X, of course, is going that direction. Then do you have your force due to kinetic friction? I'll just draw it down below here, obviously opposing FAP-X. So we do know that F net equals FAP-X minus FK. And that's going to be mass times acceleration. That's going to be FAP times cosine, sine of, yeah, because you're, the angle is actually going to be right there, because if you're going 29 below the horizontal, you're going 29 below that way, so 29 degrees will be right there. So in this case, we're going to be using the cosine of 29 degrees, which we've done anyway, and minus our frictional force, which is 48 newtons. Okay, we do know the mass, which is 16. And we obviously have to get the acceleration, which I don't know, and the applied force, which I also don't know. So the two things we don't know here. So now let's consider the perpendicular forces. You do have Fn going that way. Okay. You do have weight due to gravity. And you have FFy.
Mr. Almashi,
Yeah, go ahead.
is the acceleration 0 because you're going at a constant
Yes.
velocity?
Thank you for catching that. Thank you. So actually, then we don't even need this. Then we're actually all set. So now I could solve for FAP. So I'll move the 48 over and divide by cosine 25. So yes, now we're rolling here. Yeah, because I was about to say I was going to get stuck. I was like, I don't know what to do after that. So thank you for catching up. So 48 divided by cosine 25. Sorry, 29 degrees. So you should get 54.9 newtons. So that's correct. Then to get the work done by the pushing force, that's going to be 54.9 times 22, which is, oh, but it has to be in the x direction, my bad. So it's going to be 54.9 times cosine 25, then times, yeah, times 22, but times cosine of 25 degrees, so times 22. Yeah, you do get, well, I don't get 1060. 54.9 times cosine 25. Yeah, I got 1094. Did anyone get 1094? Yeah, that's weird. Because you're pushing force. Yeah, because if your magnitude of the force shock exerts 54.9, but you're doing it with the horizontal, so you got to do cosine of 25. Yeah, I'm a little bit confused why that's off a little bit.
Mr. E, isn't it cosine 29?
Oh, 29. Why did I keep doing 25? This is a previous problem. You're right. So it is 1060. Close enough. I got 1056. But the frictional force is going against, is just going the opposite direction. So that's why it's just negative, because it's just, and then the gravitational force, because gravitational force is going the opposite direction. It's going perpendicular to the motion, so that's why it's just 0 for 9. So that's that one there. Okay, let's keep moving. Let's look at 10.
Wait, how'd you get B again?
Oh, 54.9. So your force that we got from part A.
Yeah.
Times your distance, which is 22.
Oh, okay.
Times cosine 29 degrees. I was doing 25 for some reason. I don't know why I'm doing that. So, and then C is just going to be the opposite because it's just going against the pushing force. So it's going the other direction. D is 0 because gravitational force acting downwards, which is purely perpendicular to our motion, which is 90-degree angle. And cosine 90 is 0. So that's why you get 0 for D. 10 is going to be very similar, actually. Calculate work done on a 1,500 kilogram elevator car by its cable to lift 40 meters at constant speed again, okay? Assuming friction averages 100 newtons. Okay, so calculate the work done. So in this case, what we want to do so it's being lifted up. So I guess what we'd have to realize is that our tension, so you have an elevator here. We also have friction with the cable. It's going at constant speed as well. So let me calculate this really quickly. 1,500 times 9.8 minus 100 times 40. Yeah. Hold on a sec here. And plus 1,500 times 40 times 9.8. 100 times 9.8 plus 100 times 40. Yeah, so here's what's happening. So this is the free body diagram. So tension minus W minus Fk is essentially going to be our net force that this experiences. But really, we just want to get the tension here because that's the work it's doing. So we assume right now it's just kind of keeping everything in place. And it's doing it at constant speed, by the way. So your net force actually is 0. So now we can solve for our tension. Tension minus 1,500 times 9.8 minus 100. So tension of the cable will actually be 14,700 if you do it all correctly in the calculator. So that's the force we're going to work with. And this is not done in any angles, so you can use 0 degrees if you like. Work is equal to your force times your distance times your cosine of your angle. But our angle is just 0 because, again, there's no angle we're dealing with. So it's going to be your force, which is 14,700 newtons, because that's what the tension we're seeing in the cable that's pulling the elevator. Times distance it travels, which is, of course, 40, and times 1, because cosine of 0 is just 1. So if you do that correctly, you should get 592,000 joules, which is 5.92 times 10 to the 5th joules. And there was work done to lift by the gravitational force in this process. So you're just looking at the weight, so that's easy. Your work is just going to be your weight, your force due to gravity, times distance times cosine theta. Your force due to gravity, again, is just going to be 1,500 times 9.8 times 40. So you will get, and it's going downwards, by the way, mind you. So we can put negative 9 for the acceleration. So you will get negative 588 thousandths for that joules. So it explains that one. What is the total work done on the lift? Well, the thing is that overall your net force is 0. So you're looking at F net in this case. So this was F tension, the tension, that was for part A, because that's done by the cable, that's tension, gravitational force, Fg, and the total, you're gonna have to use F net, but our F net was 0, right? And that's why it's gonna be 0 times 40 times 1, so you get 0. So I think we have to pay careful attention to the wording. Calculate the work done in the elevator by its cable. The cable is a tension. We use that force. The next one is the gravitational force, which is weight due to gravity. The last one, the total work, we use the net force, which was 0 because you're at constant velocity. In order to get the tension, we had to do T minus W minus Fk equals F net. We know this because that's going to be parallel to our motion. The elevator is going up and down. As the elevator is pulling it up, you have two forces acting against the tension of the cable: the weight due to the elevator itself, and the friction between the cable and the elevator as it's pulling it up. And of course, our net force is 0 because constant speed. So that's how you get the tension, and then we use that for part A. And then part B and C, just pay careful attention to the wording that you're using the right force. So it is very, very detail oriented with the wording. You have to pay careful attention to it. Okay, so now let's walk you guys through 1, 2, 3, 4, and then we will, excuse me, and then we'll do some more practice. So if you look at number 1, a box is being moved with velocity v by force p parallel to that velocity along a level horizontal floor. Okay. Normal force is Fn, the frictional force is Fk, and the weight of the box is mg. Decide which force do positive, 0, or negative work. Okay, so this one should be pretty straightforward. You do a drawing. You have your box. Fn, of course, is this. Weight of the box, of course, is mg. So we'll call it W for, well, actually, we'll say mg now, just so we don't get confused with work, and Fk. And it's moving parallel to the horizontal floor. So Fk does negative work because it's opposite the motion of the box. Fn and W are both, or mg, are both 0. That's because they're perpendicular to the motion. 90 degrees and cosine 90 degrees equals 0. So that's the reason for number 1. So try and be very consistent, be a bit mathematical at the same time to back up our answers. For 2, a sailboat moving at constant velocity. Is work being done by net external force? No. The reason why that's no is because constant velocity. Remember, F net but A equals 0 because of that. So the answer is no. For B, recognize that the wind propels the boat forward and the water resists the boat's motion. What does the answer part A imply about the work done by the wind's force compared to the work done by? So they're going to be equal magnitude, but opposite in sign. Because they're counteracting each other. Kind of like what we saw over here for number 7. For number 3, a slow-moving car may have more kinetic energy than a fast-moving motorcycle. How is this possible? Mass. What if the car is very, very heavy? And remember, kinetic energy is 1/2 mv squared. The v is more impactful because you're squaring it, but mass is still involved in kinetic energy. So what this is a tank compared to a road bike or something, or just a dirt bike. That's the reason why. And then for 4, work done in a system puts energy into it. Work done by a system removes energy from it. Give an example. So I guess you could say an air conditioner might be a good example. So clearly, there's some sort of motor inside your air conditioning unit, and there's also like a lot of other stuff going on there. There's like Freon and other stuff, and it's pumping out cool air into your house. So that's work, so AC unit. Bringing in cool air requires energy. I mean, your energy bill is going to be high as a result. Now, work done by system removes energy. So this is putting energy into it. How about work done by system removing energy? I would say check the back of the AC. It's going to be really hot. That's because it's removing heat. So in a way, that's a way you're removing energy also. Another good example would be a refrigerator. Refrigerator keeps your food cool, right? But check the back of it. It's going to be really, really hot, right? It's removing all that heat. So you have that motor inside, but it's, in order to keep it cool, it's got to remove. So those are some examples you could use if you like. Okay, before we go back to breakout rooms again, any questions whatsoever? Nope, okay. So let me go and clear all drawings. Give you guys a chance to do more of these problems here. So 11, obviously you're using the diagram here. That should be pretty straightforward. You have the distance, you have the force, but you're gonna have to use a cosine, so that shouldn't be too hard to figure that one. You should be able to get the answer just fine. 12, do convert the units, kilometers per hour. Actually, hold on a sec. You might be okay, because they both use kilometers per hour. No, you have to convert, because they're asking you to calculate them. So yes, you will have to do a conversion. So remember, kilometers per hour. 1 kilometer is 1,000 meters. And 1 hour is 3,600 seconds. 13, how fast must it go, blah, blah, blah. Meters per second. So you want the speed there. So that's pretty easy because you have the formula, so you should be able to figure 1/2 mv squared. Don't worry about part B. We don't care about that one. For 14, yeah, they do give you conversion, which is nice. Do you give you the distance? Do you give you the mass, the initial speed? I guess is this coming to yeah, bring it to rest. Okay, so you should be able to get the acceleration from that. And hold on, is there any more we need to know about this part? Yeah, so yeah, I'll let you guys kind of battle through that one. 15, 16, I'll just let you guys do it. So I could keep talking about it. So you guys are gonna do 11 through 16. I'll give you guys about 20 minutes. We'll discuss, and we'll have a little discussion on 3-2. So 11 through 16 is what we're gonna work on. Put you guys in your breakout rooms. Stop the recording.